Hello everyone, my name is Madlena Ivanova and today I'm going to go over some classification methods for recommender systems, in particular decision trees, naive Bayes and support vector machines. I'm using the book called Recommender Systems Handbook. So first I'm going to start with a quick overview for today's presentation. I've broken down the presentation in 6 main sections, where I'm going to start with an overview of the main classification techniques, followed of an explanation why I have chosen to dive into 3 specific methods in greater detail. Then I'll give an explanation of the logic behind the concept of decision trees. Next I'll explain and illustrate with an example how Bayesian classifier works. Furthermore, support vector machines will be explained and illustrated with an example as well. Before jumping into the conclusion, I'll go over some common metrics that are used for evaluation of the models at hand. Finally, I'll do a brief summary and explain when we should use these classification methods. So let's start with the definition of a classifier. Classifier is called the mapping between a feature space and a label space, where the features represent characteristics of the elements to classify and the labels represent the classes. A restaurant recommender system, for example, can be implemented by a classifier that classifies restaurants into 2 main categories, good or bad, based on a number of features that describe it. There are a few types of classification, but in general we'll talk about either supervised or unsupervised classification. In supervised classification, a set of labels or categories is known in advance, and we have a set of labeled examples which constitute a training set. Recommender systems typically apply techniques and methodologies from other neighboring areas such as human-computer interaction and information retrieval. However, most of these systems bear in their core an algorithm that can be understood as a particular instance of data mining technique. Today I'm going to do an overview of some of the main classification techniques used in the context of recommender systems, decision trees, Bayesian classifiers, and support vector machines. As you can see, these are not the only classification methods that we can use, but for the sake of diversity of machine learning methods presented today, the ones listed were chosen. So when talking about decision trees, I'm sure that most of you are familiar with that concept. They're a popular method of creating and visualizing predictive models and algorithms. In general, decision tree is a type of supervised learning algorithm. It's a classifier on a target attribute or class in the form of a tree structure. The observations or items to classify are composed of attributes and their target value. Before we cover the more complex aspects of decision trees, let's examine some key terms. So in the table here, column Z is the target indicator, called also target variable, which is the piece of information that is being predicted by the model. The data in columns A, B, and C and so are called indicators. The indicators go under the names features or dimensions, and they are data points that are used to make predictions. As a whole, the total collection of indicators forms an indicator vector or feature vector. Rows 1, 2, and 3 represent the instances. They're also called atoms. If you look at the tree representation on the right, the first node on the tree is called root, and this is further divided into 2 or more homogeneous sets. You can refer to them as nodes. The final terminal nodes are called leaves. This type of classification works with categorical and continuous inputs and outputs variables. Some of the most well-known algorithms are CARD, D3, C4.5, SLIQ, and Sprint. So as methodology, as I mentioned previously, building a predictive model involves first training the model and building the tree by using known data and verifying its accuracy and reliability by using the model on test data. This test data had been set aside previously to predict the known test outcomes. When building the tree, we start at the root and split the atoms into smaller subsets of atoms. Each subset should be as distinct as possible in terms of the target indicator. This goal is achieved by iterating through each indicator as it relates to the target indicator, and then choosing the indicator that best splits the data into two smaller nodes. Splits can be decided by maximizing the information gain, defined as the formula that you can see, where ki are values of the attribute I, and is the number of observations. V of j is the jth partition of the observation according to the values of attribute I. And finally, the capital letter I is a function that measures node impurity. There are different measures of impurity. We can use Gini index, entropy, and misclassification error. Decision tree induction stops when all observations belong to the same class, or when impurity of the leaf nodes equals to 0. For practical reasons, however, most decision trees implementations use pruning, by which a node is no further split if its impurity measure or the number of observations in the node are below a certain threshold. The main advantages of building a classifier using a decision tree is that it's inexpensive to construct, and it's extremely fast at classifying unknown instances. Another appreciated aspect of decision tree is that they can be used to produce a set of rules that are very easy to interpret even from people that don't have any analytical knowledge, because it's just graphical representation. Another thing is that this method requires less data cleaning compared to some of the other modeling techniques. It's not influenced that much by outliers and missing values. The data type is not a constraint, which means that it can handle both numerical and categorical variables. And also, it's a non-parametric method, meaning that decision trees have no assumptions about the space distribution and the classifier structure. There are a couple of disadvantages. One is that overfitting is one of the most practical difficulty for decision tree models. This problem gets solved by use of random forest, which we'll discuss some other day, I guess. While working with continuous numerical variables, decision tree loses information when it categorizes variables in different categories. So it's not fit for continuous variables. Decision trees may be used in a model-based approach for commander systems. One possibility is to use content features to build a decision tree that models all the variables involved in the user preferences. So there's the idea to construct decision tree using semantic information available for the items. The tree is built after the user has rated the items, and then the features for each of the items are used to build a model that explains the user's ratings. As it could be expected, it's very difficult and impractical to build a decision tree that tries to explain all the variables involved in the decision-making process. So we might use decision trees to model just a particular part of the system. Let's take a recommender system for online purchases that combines the use of association rules and decision trees. So in this case, a decision tree is used as a filter to select which user should be targeted with recommendations. In order to build the model, we should create a candidate user set by selecting those users that have chosen products from given category during a given time frame. In their case, the dependent variable for building decision tree is chosen as whether the customer is likely to buy a new product in the same category. A similar approach combining decision tree and association rules is used for just simplifying the recommendation rules. We can use decision trees in recommender systems for item ranking as well. A Bayesian classifier is a probabilistic framework for solving classification problems. It's based on the definition of conditional probability and Bayes' theorem. The Bayesian school of statistics uses probability to represent uncertainty about the relationships learned from the data. In addition to the concepts of priors, it's very important as they represent our expectations of prior knowledge about what the true relationship might be. In particular, the probability of a model given the data posterior is proportional to the product of the likelihood times the prior probability. The likelihood component includes the effects of the data, while the prior specifies the belief in the model before the data was observed. In our case, probability of C given X is the posterior probability of a class C. This class C is our target variable, given predictor X, which is our attributes. Probability of C we'll call the prior probability of a class. Probability of X given C is the likelihood, which is probability of predictor given class. And finally, probability of X is the prior probability, or predictor. So there are two types of Bayesian classifiers. We have naive Bayesian classifier, or we can have also network of Bayesian classifiers, Bayesian belief network. In the methodology process, we have two main phases, which is learning phase and decision making. So as the methodology process, I think that by just giving you a quick example, a very brief example, it's going to be much easier to explain how the process works. So first, in the learning phase, we want to compute the probabilities of each of these categories: outlook, temperature, humidity, wind, according to our target variable. So we take all of the distance instances, like for example, if you take outlook, we take sunny, overcast, and rain, and we compute the probabilities for the person that have been playing tennis and the person that haven't been playing tennis. Our idea is that once you have a new instance, let's say x prime, which says that the outlook is sunny, the temperature is cool, the humidity is high, and the wind is strong, and we have to predict if a person is going to play tennis or no. So how do we do that? So as a first step, we look up the tables archived in the learning phase. We already computed all of the probabilities for every category and every distinct instance from this category. So in the decision-making process, to compute the probability of a person that played given certain instances, we take all the computed instances, multiply them together, and then we multiply that with the probability of play equals yes. Then we do that the same with the negatives. We take all of the instances given that it was sunny and person didn't play, it was cool, person didn't play, etc. And we multiply that whole thing by the probability of play equals no. Then we look at the final numbers, we compare them, and we can see that the probability of a person that, given all of these instances, tends to be negative. So our prediction will be no, just by comparing these two probabilities. So it's worth mentioning the difference between Bayesian classifier and Bayesian network. The Bayesian network is probabilistic graphical model. So this model represents a set of variables and their conditional dependencies via a directed acrylic graph. So for example, a Bayesian network could represent the probabilistic relationships between diseases and symptoms. So given symptoms, the network can be used to compute the probabilities of the presence of various diseases. So the Bayesian network has a lot of pros. It's very fast and easy to implement, very easy to understand. It can handle multi-class prediction, which is important. It's robust to isolated noise points and irrelevant attributes. It can handle pretty well missing values, and in addition to that, the Bayesian belief networks can handle incomplete data and are robust to model overfitting. However, there are a few cons. So the Bayesian networks, they do the assumptions that the different categories are independent to each other, which in many cases is false. So in these cases, it can be considered as bad estimator also. Bayesian networks are expensive to learn and update the model when having a lot of users. So in the recommender systems application, this is a big factor. So the application of these classification techniques in recommender system is really interesting. We can combine it with collaborative filtering together And when we do that, we can build a recommendation system that uses machine learning and data mining techniques to filter unseen information and predict whether a user would like a given item or resource or not. The Bayesian classifier is very good for incorporating user control and improving performance, especially in co-star situations where we have missing users' information, or we have like a new user introduced to our system and we don't know anything about them. On the other side, we can use the Bayesian classifier in a rule-based approach. We use it to compute the likelihood that the viewer will like or dislike a particular TV program, for example. We approach the problem with a two-class Bayesian decision model, where a show belongs to either the class watched or the class not watched. The user profile in the Bayesian context is a collection of attributes together with a count of how many times an attribute occurs in the positive and negative examples. From this profile, we first compute the prior probability that a show belongs to a particular class, and then the conditional probability that a given feature will be present if a show is in either of the two classes. Using these probabilities, we finally compute the posteriori probability for a new show, given its feature set that it belongs to a particular class. The Bayesian network approach has been used in several settings as a way to add domain knowledge for the information filtering, but as we already mentioned, it's very expensive to learn and update the model when it has lots of users. Support vector machines, or SVM, is discriminative classifier formally defined by separating hyperplane. Given labeled training data, it's a supervised learning process, the algorithm outputs an optimal hyperplane which categorizes new examples. So, SVM work by transforming the training dataset into a higher dimension, which is then inspected for the optimal separation boundary or boundaries between classes. In SVM, these boundaries are referred to as hyperplanes. You can see on the picture down what we call hyperplane, that's the red line, which are identified by allocating support vectors, or the instances that most essentially define classes and their margins, which are the lines parallel to the hyperplane, defined by the shortest distance between a hyperplane and its support vectors. So consequently, support vector machines are able to classify both linear and nonlinear data. The grand idea with SVMs is that with high enough number of dimensions, a hyperplane separating a particular class from all other classes can always be found. That's an important notion here. In SVMs, we typically use continuous random variables. In case we have categorical, we can utilize that by demicoding them. Notice that adding more training instances of the margins will not affect the decision boundary at all, because it's fully determined by the support vectors. Additionally, the support vector machines are two types: linear, when the data is linearly separated, and nonlinear, when the data is not linearly separated and we have to apply the Carnot trick. If we strictly impose that all instances will be off the margin and on the right side, this is called hard margin classification. There are two main issues with it. First, it only works if the data is linearly separable, and second, it's quite sensitive to outliers. So look at the figure on the left. You'll see that we have just one additional outlier in our ARIES dataset, so it's impossible to find a hard margin. And on the right side, the decision boundary ends up very different from the case where the data is linearly separable, as the first image we saw on the previous slide. To avoid these issues, it's preferable to use a more flexible model. The objective is to find a good balance between keeping the margins as large as possible and limiting the margin violations, or instances that end up in the middle of the margins, or even on the wrong side. This is called soft margin classification. The linear support vector machine classifier model predicts the class of a new instance X by simply computing the decision function of the transpose feature vectors with the training data plus the bias. If the result is positive, the predicted class is the positive class, or else is the negative class. You can see the y-hat equation down here. Usually the margin boundaries lines represent the points where the decision function is equal to 1 and minus 1. They're parallel and equal distance to the decision boundary, forming the margin around it. So training a linear support vector machine classifier means finding the value of W and B that make this margin as wide as possible while avoiding margin violations and limiting them. So in general, the smaller the weight vector is, the larger the margin. So we want to minimize the norm for W to get the large margin. However, if we want to also avoid any margin violations, then we need the decision function to be greater than 1 for all positive training instances and lower than minus 1 for negative training instances. Fortunately, when using support vector machines, you can apply an almost miraculous mathematical technique called the Carnot trick. It makes it possible to get the same result as if you added many polynomial features, even with very high degree polynomials, without actually having to add them. So there is no combinatorial explosion of the numbers of features, since you don't actually add any features. For example, suppose you want to apply a second-degree polynomial transformation to a two-dimensional training set as the one you can see. Then we train a linear support vector machine classifier on the transformed training set. The most right box shows the second-degree polynomial mapping function phi that you want to apply. Please notice that the transformed vector is three-dimensional instead of two-dimensional. Now here's the key insight. If you apply the transformation phi to all training instances, you don't actually need to transform the training instances at all. Just replace the dot product with its square. The result will be strictly the same as if you went through the trouble of actually transforming the training set, then fitting a linear support vector machine algorithm, but this trick makes the whole process much more computationally efficient. This is the essence of the Carnot trick. Now here is a list with some of the most commonly used Carnot transformations. The support vector machine classifier has pretty good accuracy level. It works very well with smaller and cleaner datasets, and it can be more efficient because it uses a subset of training points. However, it cannot work very well on larger datasets since the training time goes up. It's also less effective on noisier datasets with overlapping classes. As for the application of the support vector machine classifier into the recommender system context, we can use it for selecting the best pre-processing technique, for example, for predicting missing values for a support vector machine-based recommender system. We can use support vector machines to build a TV program recommender system, for example. So let's say we decide to use the electronic program guide as features, but in order to reduce features, we remove words with lowest frequencies. So furthermore, in order to evaluate different approaches, we use both the Boolean and the term frequency inverse document frequency. These are weighting schemes for the features. In the former 0 and 1 context, we use that to represent the absence or presence of a term on the content. So in the latter, this is turned into the term frequency inverse document frequency numeric value. So lastly, we can take different approaches and to use the support vector machine for recommender system in a collaborative filtering setting. The most commonly accepted evaluation measure for recommender system is the mean average error, or root mean squared error, of the predicted rating and the measure one. These measures compute accuracy without any assumption on the purpose of the recommender system. Accuracy is defined as the ratio between the instances that have been correctly classified as belonging or not to the given class and the total number of instances. So in order to evaluate a model, we usually take into account the following measures. True positive, which is the number of instances classified as belonging to class A that truly belong to class A. True negative, number of instances classified as not belonging to class A and they actually don't belong to that class. False positives, number of instances classified as class A but that do not belong to class A. And false negatives, instances not classified as belonging to class A but actually they belong to class A. So precision is defined as the measure of how many errors we make in classifying samples as being of class A. On the other hand, recall measures how good we are in not leaving our samples that should have been classified as belonging to that class. So please note here that these two measures are misleading when used in isolation in most cases. So we could build a classifier of perfect precision by not classifying any sample as being of class A, therefore obtaining 0 true positives but also 0 false positives. Conversely, we could build a classifier of perfect recall by classifying all samples as belonging to class A. As a matter of fact, there's a measure called F1, measure that combines both precision and recall into a single measure. Sometimes we would like to compare several competing models rather than estimate their performance independently. In order to do so, we use a technique called Receiver Operating Characteristics, or ROC curve. A ROC curve characterizes the relation between positive hits and false alarms. The performance of each classifier is represented as a point on the curve. As you can see in the image here, usually the further away to the left corner the graphic is, the better the model performs. So in this case, we can say that model 1 performs much better than model 2. The confusion matrix is often used to describe the performance of a classification model on a set of test data for which the true values are known. It's also very good visual representation. In the presentation, I gave you an overview of 3 classification techniques and their application in the recommender system context: decision tree, Bayesian classifier, and support vector machines. However, here comes the question, how are they similar or different, and when should we use them? So first, comparing the input types. If you're trying to predict a categorical value like red, green, or if you are trying to predict a continuous value like 2.9, 3.4, then decision tree will handle both problems. Also, the Bayesian classifier is good in handling the categorical and the Boolean data types. Support vector machine, on the other hand, is good in handling Boolean and continuous random variables. It can handle also categorical, but we have to demicode it. As a machine learning category, they're all from the supervised learning family, meaning that we need to train them on labeled data first. If we're interested in very high accuracy and the data is not too large, then we should use support vector machines. If you're trying to solve for speed, then we might want to use decision trees. Naive Bayes, on the other hand, is pretty fast too. In the recommender system context, we can use them in the pre-processing phase or in the actual modeling phase. We can use them for filtering at the end. So there are different places where we can use the decision tree, the naive Bayes, and the support vector machine. There is no just one place for each of them that is conclusive. So as takeaway from today's lecture, please keep in mind that when you define a problem, you make sure you answer the question, what problem do you want to solve? What is your input and what is your output? And start from there. What are your main objectives? Start simple, be familiar with the data and the baseline results, and then build the complexity on top of it as you go. Thank you for your attention, thank you for listening, and have a great afternoon.